Hey students! In this video you will be able to learn about electron affinity, its definition and chemical equations to understand the process. Also I'll describe and explain the trend in electron affinity when descending groups and across periods in the periodic table. So let's begin, students. Chemists have a tough job keeping track of how much energy there is in the system, and all the different types can be exhausting. One of the ways chemists make it easier is to break things into smaller steps. If we have an atom, we can measure the energy required to remove each electron one by one until we have a bare nucleus. We call the process of removing these electrons ionization. Here are the first and second ionizations of a helium atom. Kids. But what about the opposite? It's possible for atoms to gain electrons as well. So what do we call that? Here is an atom of hydrogen. When a hydrogen atom is close enough to an electron, they'll attract each other a little and they'll stick together. Chemical potential energy will be converted to other forms of energy like heat. The energy released in this process is known as the electron affinity of hydrogen, students. Word electron affinity refers to the overall process of adding electrons. Electron affinity is defined as the energy released when an electron is added to a neutral atom in the gas state to form a negative ion, and we usually express electron affinities in kilojoules per mole of atoms. Since we are talking about a change in energy, when an electron is added to an atom, there is an equation used to determine the electron affinity. This equation shows that electron affinity is equal to the negative change in energy. For example, the electron affinity of fluorine has the negative sign, which shows us the energy that is released to add one electron to an atom. The giving off of energy is shown with a negative sign, students. Now, there are two factors that can affect electron affinity. These are atomic size and nuclear charge. The smaller the atom is, the closer the outermost shell is, therefore, it is a stronger attraction between the nucleus and the incoming electron. That means the electron affinity is higher for smaller atoms. Nuclear charge also affects electron affinity. The nuclear charge is also known as the atomic number, which is the same as the number of protons. Protons are positive subatomic particles. The more protons there are, the greater the attraction is to electrons. Students. Based on this sign convention, this means that a higher electron affinity indicates that an atom more easily accepts electrons. A lower electron affinity indicates that an atom does not accept electrons as easily. Students. There is such a thing as a second electron affinity, where the electron is added to a 1- ion instead of a neutral atom. We'll have a quick look at this later, but we're going to focus more on first electron affinities, students. Now let's take a closer look at the trend going left to right across a period. Let's take a closer look at period 2. As we go left to right, the atomic number increases. Since the number of electron shells is not increasing and the nuclear charge is increasing, the atomic radius goes down. In an atom of lithium, the nucleus has a charge of 3+, so we have 3 electrons in the electron cloud. In total, these electrons have a 3- charge. Meanwhile, a fluorine atom has a 9+ charged nucleus and 9 electrons. For this trend, we're going to ignore the noble gas neon. Kids. It's important to mention that noble gases are not included in the trend for electron affinity. Since we already know it's very stable and won't accept an extra electron. Students. Now let's imagine this extra electron being introduced next to a lithium or a fluorine atom. The electron approaching a fluorine atom can get much closer to the nucleus before being repelled by the electrons. So this is a basic explanation of why, in general, we see an increase in electron affinity going left to right across a period of the periodic table, students. Let's see anomalous behavior of beryllium, nitrogen, and neon. Students. Alkaline Earth's metals have filled s subshell which discourages addition of an electron. Ea values are nearly zero. Beryllium negative would not be stable, because the added electron is assigned to higher energy subshell 2p than the valence electrons 2s. Kids. Electron affinity of nitrogen is 0 due to its half-filled configuration of 2p orbital, np3, which gives stability to it. Half-filled shell discourages addition of an electron, Ea values less negative than neighbors. Thus its electron affinity is 0. Last but not the least, in case of noble gases. Completely filled shell, np6, strongly discourages addition of an electron, students. Now let's look at the trend going down a group. As we go down a group on the periodic table, atoms of the elements get bigger and bigger and bigger as they have more electron shells. With similar elements, as the size of the atoms increases, the attraction to an extra electron will decrease. If we try to add an electron to a small atom, it'll be able to get closer to the nucleus, while for atoms with more electrons, the electron won't be able to get as close. Before we move on, we are going to look at one inconsistency in group 17. Fluorine has an unusually high electron affinity at 328 kilojoules per mole, but chlorine's is even higher. Meanwhile, the electron affinities of bromine, iodine, and so forth continue as expected, following the downward trend. While it's hard to know exactly why this happens, we can come up with a decent theory. Students. Reason for anomalous behavior of fluorine is that a fluorine atom has a tiny atomic radius of only 42 picometers. Chlorine's is almost double at 79, while those of bromine and iodine increase incrementally. Here is one atom of fluorine, 9 electrons surrounding a nucleus with a 9+ charge. A fluorine atom is even smaller than a hydrogen atom, which has an atomic radius of 53 picometers. We can imagine that the negative charge of those electrons in a fluorine atom will be very, very dense. So, this is going to reduce the electron affinity of fluorine relative to chlorine because the incoming electron is experiencing greater repulsion. Students. The last thing we're going to look at, and I said we'd go back to it, is second electron affinities. Second electron affinities are associated with this process. X negative plus an electron forms X2 negative. Again, this happens in the gas phase. The interesting thing here is that we're introducing an electron which is negatively charged to an anion. So the negative ion will naturally repel the electron, raising the energy required to add them together. Because of this, second electron affinities are always negative and therefore endothermic, students. We can see this with the element oxygen. The first electron affinity of oxygen is about 141 kilojoules per mole. The enthalpy change for this process is negative. We're dealing with an exothermic process. But the second electron affinity of oxygen is predicted to be about negative 744 kilojoules per mole. So the enthalpy change for this process is positive. We're dealing with a vastly endothermic process, students. Let's finish up with the key points. Electron affinity of an element is the energy released when an electron is added to a neutral atom of that element in the gas state to form a negative ion. Electron affinities are normally expressed in kilojoules per mole. Electron affinity is often used to refer to the process itself, adding an electron to a gaseous atom. An element's second electron affinity is the energy associated with the process of adding an electron to an ion with 1- charge. Kids. On the periodic table, we see a trend of increasing electron affinity generally moving left to right and bottom to top. Within a group moving bottom to top, we attribute this trend to a decreasing atomic size. And across a period, an increase in atomic number of the element means that the atom will have a higher nuclear charge. This contracts the electron shell and allows the incoming electron to get closer, being more attracted to the nucleus. Bear in mind that often we ignore the noble gases when discussing these trends because noble gases have atoms with full valence shells. They're extremely stable, and adding electron will always be endothermic. Thank you for watching. Stay blessed.